Hello, and welcome back to the course. So we're talking about power series. This is section 2.3 in the book, and this is the second part. We'll have another part on power series. All right, so power series, as we said last time, is this sort of an object. It's a series of powers. Now let's define this number r by this expression over here, 1 over the lim sup of the nth root of the modulus of Cn as n goes to infinity. And here we interpret 1 over infinity as 0 and 1 over 0 as infinity, just so that we don't have to rewrite this thing. It's not quite, it sort of looks like it would be the extended real sense because everything is real, but that's not what we're doing here. We're really doing sort of the Riemann sphere sense or the positive real sense, extended positive reals. So that's kind of common, but so that we don't have to rewrite these cases separately. All right. So now let little r. So basically, we're gonna move z, right? P is fixed, and we're gonna move z and see where this power series converges, right? So for simplicity, let little r be the distance from z to p. Now, by the root test, this guy converges if this lim sup is strictly less than 1, right? When is that true? Well, let's massage this a little bit. We have this r to the n here. We're taking the nth root. So that really comes out. There's no n in there anymore. So it's just r times this lim sup. That's this lim sup over here. Therefore, I can rewrite that. Therefore, the lim sup is 1 over r. So I have this as r times 1 over capital R, right? That's supposed to be strictly less than 1. If that's strictly less than 1, then the series converges, right? So that means that this series converges absolutely, right? Because it converges with these guys, right? This guy converges. Whenever r, which is the distance from z to p, is strictly less than this capital R over here. Now, if this ratio is strictly bigger than 1, then for infinitely many n, we're gonna get that the absolute values here, right? If you take the absolute the modulus here, this guy, because because of the lim sup, right? I mean, you have to sort of break it infinitely often, right? You'll actually get strictly bigger than 1 here, right? So that means that in that case, this guy will diverge, right? It cannot converge. I mean, you cannot, a series, if it converges, its terms at least go to 0, right? So they can't, infinitely often be bigger than 1, right? So the series diverges if you're further away than capital R from P, right? So we've proved the Cauchy-Hadamard theorem, that the power series converges absolutely if you're within capital R of P, and it diverges if you're further away, right? By the way, it's Hadamard published this in his thesis like 50 years after it appeared in one of Cauchy's papers. So somehow must have not seen it, right? But he still has his name on it. So all right. So graphically, what that means is that we have a P, and we have a disk of radius capital R. Possibly infinity if it's infinity, or 0 if it's nothing if it's 0. But if it's some finite number, then it's this nice disk, and the series converges absolutely inside and diverges. There's no absolute divergence. Diverges outside. Right, that's what I said. Diverges on the complement of the closure and converges inside. Now, doesn't say anything about the boundary. Yeah, that's tricky. You have to, if you want to know if some power series converges on the boundary, you have to be, that takes a lot more work. And again, R equals 0 just means it doesn't converge anywhere. Well, except at P, but we're saying that's kind of a fake convergence, right? And R equals infinity means it converges for all Z, right? Because any Z is distance less than infinity from P. All right. Now, so the R, this capital R, is called the radius of convergence. And it's called the radius because it's the radius of this circle, right, of this disk. Now, there is a very nice test for convergence. Say this if and only if, but it's really used mostly in one direction. One direction is easy, and the other direction is the interesting one. But we have that a series is a power series converges in some disk of some radius capital R, if and only if for every R, you have to take something smaller than capital R, but for every R, less than capital R, there exists an M. This M can depend on the little r, such that you get this estimate over here. That's supposed to be true for all n, of course, right? In other words, this sequence, the modulus Cn times r to the n, is bounded whenever r, little r is less than capital R, right? Now, if we stick in the capital R, that's not necessarily true, especially if it's that, well, when that capital R, not especially, when that capital R is the radius of convergence. So for example, we have the geometric series, we've seen that before. And this guy over here, which is modified a little bit, we stick an n in there. Both of these you can compute have radius of convergence 1. So they converge in the unit disk and diverge outside the unit disk. However, the sequence of coefficients, right? I mean, here, capital R is 1, right? So this would be just the sequence of moduli of the coefficients, and they're all positive, right? So it's just the sequence of coefficients, and they're all 1 here, and they're n here, right? So in the first case, they're bounded, they're all 1, and in the second case, they go to infinity. So they're not bounded. However, if R is less than 1, then n times r to the n is bounded. So, all right. So let's prove this. So first, let's suppose the series converges, right? And let's suppose that R is less than capital R. Well, then this guy converges, right? We already have that, by Cauchy-Hadamard, right? If I'm inside the radius of convergence, I get absolute convergence, right? And therefore, if this converges, the terms must be bounded. Actually, they go to 0, right? So they're definitely bounded. Right, so that's one direction. Conversely, fix an R, right? Again, it should be an R less than capital R. And suppose that we have that this guy is bounded, and we want to show that the series converges, right? So let's stick in another radius, slightly smaller again, right? So this S is less than this R, which is less than this capital R, right? So we have these 3 circles in there, and let's look at the ratio test. So let's look at the nth root of the modulus of c to the of Cn times S to the n, right? And we really want to talk about R, so let's put an R in there. That means that I have to, I have to pay for it, right? So I can replace the R with an S, but I have to pay for it. I have to put the S over R in the front. Now we were supposing this bound over here, right? So we have S over R times the nth root of M. So we have this nice bound here. Now, if we take the lim sup of the right-hand side, well, this guy goes to 1, right? And so we get that the lim sup is actually the limit on this, here the limit will exist, right? But we're taking lim sup here. So the limit here is strictly less than 1, right? Because it is actually S over R, and that is strictly less than 1. So therefore, by the root test, we have that the series converges absolutely in this disk over here, in this closed disk of radius S, right? Now, since both S and R were arbitrary, right, the series converges absolutely in this R disk, right? Because okay, so we picked an R, we picked an S, and then we got convergence here, but we could have picked a bigger little r, just closer to capital R, and then an S closer to little r, right? And we get that way we get convergence everywhere. If I want convergence at some z, I have to pick a little r and an S that's well, really I can pick an S that's equal to the distance of my z to p, and then I just need to pick an r, little r that's between that S and the capital R. All right. So so that's it for today. Next time we'll look at uniform convergence of power series. It's the last part of section 2.3. Okay, see you next time.